Hello, I'm Marcelo Galhardo. I work in the Android X architecture components team at Google.
And I'm Jeremy Woods. I also work on the Android X architecture components team. And today we'll talk to you about some of the things that we learned while decoupling library components from the Android platform. So on the Android X architecture components team, we have about 6 different people in 3 different countries. And we own about 12 different libraries, about 10 that we work on consistently. But actually, as of Tuesday, that number jumped to 14 because we released the Navigation 3 and the Navigation Event libraries. Okay, so here's what's on the agenda. I'll give some quick motivation about why we're doing this, like specifically why we're moving the architecture component libraries to KMP. And then we'll go through a couple of the approaches that we use. So we'll talk about migrating an existing library like SavedState. And then we'll talk about how we created a new library. For this, we'll be talking about Navigation Event, not Navigation 3, I'm sorry. But the idea is to share how we decided when libraries get rewritten or when they get migrated and how we approach the work and some of the challenges that we face while we're doing so. By the end, you'll have a better understanding of the trade-offs between both approaches, whether you're migrating or creating a new library. First, a quick word on why we think it's important to migrate our libraries to KMP, and where Kotlin comes, so I don't think you'll need much motivation, but I'll do a little bit anyway. As Kotlin is the primary language for Android development, KMP is the natural next step. 6 years ago, we became Kotlin first in Android, and it's only right that we take the next step to make all of our platforms multi-platform. So by supporting KMP, we hope to reduce the duplication and maintenance by shipping a single code base for multiple platforms. And it's about setting a precedent for improving the ecosystem. We want to allow you to expand our libraries by expanding ours first. These are all the current Android X architecture libraries that we have released other artifacts for other platforms for. As of today, there are 9, and we're always considering more platforms to release here. But today we'll focus on the SavedState library as an example of migrating an existing library to KMP. And then we'll look at Navigation Event as an example of why we create a new library for KMP.
Right. Our first topic today is about migrating SavedState to KMP. If you're an Android developer, you're familiar with Android X SaveState. If you're not, a quick intro. It's a library that allows you to save and restore app state across process death. So what is process death? It's when the system kills your app process to free up resources. Before that happened, the system gives you time to save its current state. In the next launch, you get this state back and can restart your app in the same place as the user left off. The library is built around 3 key components. The SavedState registry controller, which is responsible for saving and restoring your state to and from a bundle. SavedState registry, which is responsible for reading and writing savable data into a bundle. And then the SavedState provider, which provides the actual data that should be saved into the bundle. Note that a SavedState registry controller contains a SavedState registry, and a SavedState registry holds multiple SavedState providers. All of these 3 components interact directly with the android.os.bundle to perform their tasks. In an Android app, your activity receives callback from the Android framework, like onCreate and onSaveInstance_State. Your activity then delegates these callbacks to the SavedState registry controller. The registry controller will then restore state during onCreate using the bundle provided by the framework, and the SavedState during onSaveInstance_State by writing to the bundle also provided by the framework. So how these APIs look like? Here is the API for SavedState registry controller. It has a SavedState registry, and they perform restore and perform save methods. Both of them take a bundle. Here's the API for SavedState registry. It allows you to consume a state stored in a bundle or to resist a provider for a state. The registry also contains the SavedState provider interface, which has a single method that returns a bundle. Finally, this is what the integration with a component activity looks like. The activity creates a registry controller. The controller is invoked then in the respective framework callbacks, such as onCreate and onSavedInstance_State. Or if you want a more high-level API example, the Android X view model SavedState handle. This API internally uses SavedState res to save and restore its state. So we have talked about how these APIs look like and how they're used, but why can't we simply replace these APIs with KMP variants? If we take a look at the top 50K apps, about 99% use SavedState. Breaking these APIs would be a big problem for the ecosystem, and asking all users, apps, and libraries to migrate to a new API surface would be a delicate undertaking. And also, this is the public API of a bundle. You can't actually fit that in a single slide. So if we go back to the register controller API surface, the only thing blocking this API from being converted to KMP is the Android OS bundle. So what can we do about this? Before we start migrating the bundle API to KMP, there are 3 requirements we need to keep in mind. Our first requirement is Android backward compatibility. This means making sure our new code still works with all the Android OS versions and with old versions of our libraries. The bundle is a core part of the Android framework. The framework team owns it, and it can change with new Android OS updates. Our job in the Android X team is to make sure our APIs work all the way back to Android API 23 and shield you against API change in the framework. The second requirement is keeping the bundle namespace clean. The bundle class is quite popular. It's maintained by another team, and it already has way too many functions. Adding a new extension function, for example, could introduce risks, such as polluting the API with methods that may not be useful for everyone, or shadowing existing methods, but only specific platform targets. For example, calling put integer in a common module could resolve to different implementations across different targets if we just add an extension method with this name. This happens because Kotlin prioritizes member functions over extension functions, and for a good reason. So extension functions may get ignored if a member with the same name exists in a target. The third is no additional cost. The bundle class is part of the critical path during state restoration. This means our solution must be efficient. Whatever we introduce must come with no additional cost to runtime or memory. Okay, if we go to the previous example, what if we could change the bundle to something that was not platform-specific, and we could do this without breaking API compatibility and abiding to these 3 requirements? So Kotlin has a good answer for the problem, which is expect actual. We can make a new expect class called SaveState. This class works different on each platform. As you can see, it's empty expect class. There is no methods, nothing in the public namespace of it. Like on Android, SaveState will be just another name for bundle. On other platform, it will be a simple map wrapper. And then we give you APIs to mutate this map from your common source set. You can make a new SaveState in your common source set by using the SaveState function. You can also give it an initial state using the SaveState writer in the block lambda. You can get data from a SaveState by using a reader, and you can put data into SaveState by using a writer. Just so you know, both reader and writer are inline classes and functions that wrap SaveState. So that means that the Kotlin compiler will inline this code, and there will be no new object instance created when you use it. So this is a visual representation of that structure. As you can see here, we have added a new way to do things without making the original bundle messy. We also have no new allocations thanks to Kotlin line classes and functions. And yes, this new API is also backward compatible. So in the future, if the framework team decides to add a new API, we can backport them at the reader and writer level without you having to change your code. So let's say you have a custom data class you would like to save and restore in your common code. It takes a name string and an age integer. It's John Doe, 21 years old. You can use the factory function to create an instance and write its initial state, and the read function to get any value from the save state. So now we have to take care of addressing the problem of how to convert SavedState KMP by using a bundle on Android and a map wrapper on other platforms. We also introduced the reader and writer API without polluting the bundle public namespace. So while we have a KMP solution, it doesn't quite meet what a Kotlin developer would expect from it. It's a bit verbose to call the read, write, and so on. If we look at the KMP ecosystem, there is a wide adopted solution by the community, which is the Kotlin X serialization. It's a multi-platform serialization library provided by JetBrains. Since we already use it in Android X navigation for type-safe navigation, and we had a good experience with it, it seems like a good fit for us. So we have decided to address that by implementing an optional KTX serialization codec for SavedState that allows you to use KTX serializable class as a SavedState. This is in line with the current existing codecs, such as Android X navigation codec and the Kotlin X serialization JSON codec. Any serializable class that works with any of these other codecs also work with our own. Okay, if we go back to our custom data class, person, so instead of manually writing your serialization logic now, you can just put a serializable notation on your data class, and that's it. With this, you can now use the built-in encoder and decoder for SavedState serialization. You can call encode to SavedState to transform any serializable class into SavedState. And to get your data back from SavedState, you can call decode from SavedState. Please note that if you use the encode and decode functions, if you use the encode to encode the SavedState using that codec, you also must use the decode of that codec. If the data is manually changed, the decoding may fail. And here you can see how that simple person data class will look inside the SavedState. This is a quite simple example, but it supports all the KTX serialization types. We also offer a SavedState configuration that lets you customize how the codec behavior. It follows the standards from the Kotlin X serialization configuration classes. For example, if you would like to encode default properties, you can set encode defaults to true. We also offer delegate functions that handle the serialization for you. For example, on Android X view model with SaveState handle, you can call handle.saved. You can also use it in any SaveState registry owner by calling saved. This includes activity, fragments, nav backstack entry in navigation 2, or within the content of the nav entry in navigation 3. But we can take this even further and add support for Compose. In Compose 1.9 Alpha 3, you can pass in a key serializer and a serializable class to remember savable. You don't need to write saver manually anymore. But please note that in this alpha release, you do have to pass in an explicit serializer to use the serializable class with remember savable, otherwise it won't work. And now, if you go back to our navigation tree example, we can remove the local SaveState registry owner boilerplate by using our shiny new remember savable with key serializer. And that's it.
So that was a really good look at an example of migrating an existing library that was closely integrated with the Android platform via bundle. Now let's take a look at an example where we decided to create an all-new library instead of migrating the current one. And to do that, we'll focus on the navigation event library. So navigation event is our new Android X library for handling in-app system events on multiple platforms. I know that graphic is not actually in-app. It's a system gesture, but you get the picture. On Android, this allows apps to handle events like System Back, which includes Predictive Back. And on other platforms, we also need to handle things like keyboard or browser navigation events, or even forward navigation. So why do we even need this navigation library? Well, let me provide a little context. So our current solution to Android X for in-app back is the on-back press dispatcher. It was introduced in activity in the first release of activity in like 2019, somewhere around there. And the dispatcher is always available for a component activity. So even if you don't know that you have this, like it's available from your activity if you're coding inside of activity. And then once you have a dispatcher, the only thing you ever need to do to get a system event is register an on-back press callback. And in Compose, like we made this probably way too easy because a lot of reasons. But in Compose, you just add a predictive back handler to your composition, and we do all of the work for you. The on-back press dispatcher also has integrations with lifecycle, but I'll kind of skip those right now because that's not so important. But here's an example of what non-compose usage looks like for an on-back press dispatcher. I have my component, and I would like to handle a back event. I can retrieve the dispatcher from the activity, and we'll just assume that you passed in the activity as a parameter. And then as part of the init block, it adds the on-back press callback. And this callback has all the functions you need to handle predictive back, right? So it has a handle on-back started, and this tells you when your predictive back is about to start. Progressed, so you're getting progress, you're moving your finger along. And then it has pressed, and don't ask me why this name is not completed, but it has pressed, and this fires when your event completes. And then it has handle on back cancel, so if you're doing a predictive back and you get all the way to the edge and then you decide, hey, I don't actually want to do this, you can go back. Or if like another button gets pressed or something like that, your handle on back cancel fires, right? So, predictive back is nice, and like you would need to overwrite all those for predictive back. But if you just care about back, we also offer this handy extension function for like just add callback, and this just does back for you, so you don't have to worry about any of that other stuff. And as long as the callback is enabled, the most recent callback added to the dispatcher will always receive the event, either via the predictive back gesture or 3-button nav or however you're doing your back events. So, but just to cover all our bases, that was all non-compose examples. We'll take a look at the predictive back handler in Compose because it's like pretty cool how we figured out how to do this. It just only gives you the trailing lambda, so by default you'll just look and see like, oh, it gives me a trailing lambda, but that lambda has a flow of a back event compat, which is our compatible version of the back event, and we use that requirement in coroutines. We wrote a lint rule that makes sure you collect on this back event. And that requirement, along with coroutines, we formulate all the callbacks inside this one lambda. So before you call collect, everything is treated as on start. So that just area of your code is treated as on start. Within the collect of the handle on back, within the collect is the handle on back progress. So that's where you would do whatever, you would receive the progress there and then do whatever you want to do with it. And then after collect, like, it gets kind of fancy. We wrap with a try finally statement, and so we create 2 different paths. And if the collect succeeds, so you go all the way through with your back gesture or you quick swipe or however you want to finish it, the code immediately after the collect gets called, and we consider that the on back pressed. And then if the code gets interrupted, on the back end, we catch a cancellation signal from the coroutine, and we skip the code immediately after your collect, and then we run the code in the finally block. And like, it works, like it's fine. So that's easy, right? We thought so. So we're actually happy. We're actually like happy with our API shape of both the on-back press dispatcher and the predictive back handler. But what's the problem? This API actually doesn't handle all the ways that Android does system back. So before I get into this next part, I'm gonna like take a second to give you some vocabulary. And the reason I have to do this is because naming is really hard. So as I go through the slides, you'll hear me refer to 3 different sets of dispatchers and callbacks. We just went over the on-back press dispatcher, and that is the Android X solution for on-back press. So on-back press to Android X. It like rhymes a little bit, right? The on-back invoked is actually the signal from the platform, and they copied us. We were first, right? So they just did this in API 33, and we were way ahead of that time. But on-back invoked means I'm talking about the platform, right? And then navigation event is the KMP version of on-back press in Android, right? So differentiation, those 3 different styles. Everybody understand? Clear? Okay. So Android has 3 ways of providing system back events. The first is the activity on back press function. So if you have an activity, you can always call on back pressed, and it'll fire throughout your entire system and cause you to go back somewhere. As of SDK 33, the on back invoke dispatcher allows for handling predictive back gestures. And then we still kind of support key code back historically for things like views and keyboards. But the funny thing about key code back is if you enable predictive back, this doesn't work anymore. But like we still kind of need to support it. Like there's other use cases where key code back is important. The on-back press dispatcher currently only handles 2 out of 3 of these. So key code back is completely ignored by the on-back press dispatcher. And we're still missing some important Android features, like the platform has pass-through. So imagine you are writing a library and you want some animation to work along with material in navigation. That actually doesn't work. Material just intercepts the signal altogether. And there's also things like overlays. Overlay priority. So if you're using a drawer layout and you have a dialog that pops up on that drawer layout, the dialog will follow the on-back press dispatcher, and the drawer layout goes directly to the system, and so the back will just go to the drawer layout. Doesn't work at all. So we need a way to handle all of these, and we could actually effectively kind of put these into the on-back press dispatcher API, but this is just for Android. There are any number of signals that we could need to handle for other platforms. So handling back on Android is actually just a small subset of what we need to support. Like if you look at the first side, back is coming on all platforms. And then we have this concept of up. Up is like back, but it won't exit your app. Don't tell me why we did that. And then there's forward. And forward, like if we want to support something like web, like the name back doesn't even really work anymore. Like we need an entirely new library to do that. So we came up with navigation event, a lot of naming. We took all the parts that we liked about our current system, so the owner, the dispatcher, and the callback, and we gave them a new name, navigation event, and then we created those components as part of the Kotlin common source set. And so all this entire library, most of the library, is in the common source set. And so because there's nothing platform specific about this particular part of the code. And that was easy enough, but like that's just for handling the events. How do we actually get these events to the dispatcher? And especially since they come from different platforms. And you guessed it, expect actual, the thing everybody uses for multi-platform in Kotlin. So we currently provide 2 expect classes from navigation event. There's a navigation there's a navigation input handler, and we might rename that, it's Alpha 1, which defines your platform-specific inputs. It has a reference to the dispatcher that is going to provide input to, and then it provides a single internal update active state function to determine when this input should be active. And then there's the actual navigation event, which transforms the signals from the platform into something that the navigation event dispatcher actually understands. It takes a float, like a lot of these are for phones, so touch float, where's your hand touching on the screen, how much progress you've had, a swipe edge, and this is where you can get away from the phone and you can add some things like indicators for keyboard touch and a swipe edge or something like that. And then we have this extra thing that we need to support from Android, time frame milliseconds, and this helps you calculate velocity. So if you want to do a fancy animation based on how fast somebody moves their finger, you have that possibility. So now instead of our navigation event matching the exact structure we had before, where everything was totally integrated, we have this like offset where you can add inputs from the platform. And it translates those signals into our navigation event dispatcher. So can we verify that like what we're thinking about actually works, right? So on the architecture team, we like to believe that if we're going to create a new library that we can use it, that we should be our own customer. I think this is like our excuse for continuously making libraries, but maybe not. But the idea is, can we rewrite our current on-back press dispatcher on top of navigation event library, right? And then in theory, navigation event should be flexible enough to do this since it's supposed to be our KMP solution, so it should have no problem handling the Android side. The second goal was, can we provide an integration for the new Navigation 3 library, right? So Navigation 3 is our new approach to a completely composed first navigation, and that means we need to be KMP as much as possible from the start. And the predictive back handler that I showed you earlier in Compose is part of the activity library. There's a chance that we never actually make activity KMP because activity is a very Android concept. And so instead of forcing the UI of navigation 3 to be in the Android source set, we really need a common solution for solving predictive back so that everything can be common and it just kind of works out of the box. So let's focus on the rewrite of the library first. Since we are Android X and we have to be API compatible, we're never going to get rid of the on-back press dispatcher stuff. It's going to be there for forever, and we just have to live with that. So we'll keep it there, and then the navigation event dispatcher will also, like the component activity will also become a navigation event dispatcher owner. So at the very least, you can always retrieve one from the component activity, and we like that. Like, that's been very convenient. But instead of on-back press dispatcher handling events itself, what if we could make it delegate to the navigation event dispatcher, right? And so we have that common layer where you don't actually need to change anything on your side. We just did it for you. So taking a look at our graphic from earlier, we can go from having platform-specific integrations linking directly to the on-back press dispatcher to having the navigation input handler be our platform-specific intercept, and then adding on-back press dispatcher and having it just act like a callback of the navigation event dispatcher. And it just happens to dispatch all of the events that it gets from the navigation event dispatcher into on-back press callbacks, right? So that was the goal, and that's exactly what we did. We just delegated all the on-back press dispatcher calls to the navigation event dispatcher, and then all the on-back press callbacks are delegated to navigation event callbacks. So what does this approach actually look like in practice? We know Android, so it's easy enough to try. So let's look at the actuals. A quick reminder of what the navigation event expect class look like. It's a simple class, single constructor. Like, we want to keep this part as easy as possible. And in the actual, we created a navigation event constructor, and it takes the platform-specific back event from Android. It passes all the fields from that class into this new class, and we know it's exactly what we need for Android, so this works fantastic. Like, out of the box, no complaints. For other platforms, they need to provide their own signals to convert, but now we'll take a look at the slightly more complex navigation input handler that's responsible for adding the inputs from other platforms. So here is a reminder of the navigation input handler expect class. Since we don't know what the actual other platform signals will be, it's like extremely generic right now if you look at it. For the Android implementation, the input handler takes a dispatcher, and then everything inside is platform specific. So it has the Android on-back press dispatcher, which is responsible for getting signals from the platform, and we will serve that, and that will serve as our bridge to Android. And then we need an on-back invoke callback, and we convert those events from there into navigation events. And then we have a flag to know when we need to have the on-back invoke callback registered. For the methods, we'll get the setter out of the way. Like, we just need a way for people to set the invoker so we can get the signals from Android. And then we only have two functions to implement here. The initialization function, which actually hooks up our dispatcher to the on-back invoked callback. And then the update active state, which changes the active state of the navigation input handler. So a quick look at the update active state. It has a variable for whether it should be registered or not, and that checks whether the navigation event dispatcher actually has callbacks that are listening. And then if we should be registered and we aren't, register it. And if you aren't registered and you should be, or if you are registered and you shouldn't be, unregistered, right? So very basic, very straightforward, simple. So let's go back and look at the init callback. Here's where we create the on invoked callback that we connected to the on invoke that we connect to the on-back invoke dispatcher. I told you these names. The callback immediately dispatches to the navigation event dispatcher, and then all the functions for it just do that. So most of our functions just look like this, where we're just taking the signal and then converting it and then passing it. So the on-back press callback is just a navigation event callback, and then it does all the same things. And then the on-back press dispatcher has an internal navigation event dispatcher that delegates things in the same way. You add a callback, and we get the event dispatcher from the callback, and then we add that to our navigation event dispatcher, and then all the functions just go to the navigation event dispatcher. And like this looks very simple, but this actually worked for like 95% of the cases that we had. Like when we put this into Android and like ran all of our tests. We had one problem though, because we forgot about something. On back press dispatcher has a lifecycle integration that we just never thought about or considered. And the lifecycle integration, it'll enable and disable your state based on what your lifecycle state is. So if you're started, it enables itself. And if you're unstarted, it goes back to create. And then when you get destroyed, it removes itself, right? But I won't go into too much on like how we solve this. It is solved, like it actually works right now. But we used the auto closable to address it. And because we're trying to make this library very, very unopinionated. Like we don't want to put any of our other Android X architecture components into the core library. And so we might end up creating something on top of this later, but for now, we'll just leave it where it is. And our last goal was a Navigation 3 integration, and this is probably why we write any libraries right now. So we really just want to get away from Android-specific we really want to just get away from the Android-specific activity dependency and over to navigation event. And to do that, we just kind of swapped over we swapped from the predictive back handler that we had before to a navigation event handler. The only thing we changed about the API is instead of taking a Boolean, it now takes a Lambda that produces a Boolean. And that's because we had this fun bug in Compose where if you could go back fast enough, you could get to a state where your predictive back handler was actually disabled and it still allowed you to do back because you didn't recompose in between the frames. So that got fixed in Navigation 3. And despite not changing the API much, like we've still been able to do some pretty cool animations with the new library. So like this particular animation, I think me and one of my coworkers did in like 5 minutes on Thursday. So like we didn't touch any of the particular back stuff. We just told Navigation 3 that we wanted to display 2 screens at a time, or we wanted to display 1 screen at a time. And then we started scrolling back, and like that's the animation that it gives you. So it's really nice. And the goal is that you don't have to actually write the Navigation 3 UI layer to get this. If Navigation Event had different platform implementations, you would get hopefully something like this out of the box, and then you could customize it however you wanted to after that. But we're not even close to being done with Navigation Event. We're just Alpha 1. We just released the first Alpha on Tuesday, and the only thing we really did was solve our Android problem in a KMP-friendly way. We shaped the underlying rewrite as part of the activity, so at least like everybody's already using this. If you upgrade the activity, you're using this, and you won't know unless you like actually dig into the code. But we still need to add support for keyboard events and forward navigation, and not to mention like other platforms. We still need to do that. So we'll be working closely with JetBrains and the rest of the community to like try to get this really right, and so it makes it easier going forward.
Okay. To sum up what we have talked about today, when making our library support KMP, we basically had 2 options. We could either try to migrate an existing library or could start from scratch and build a completely new one. Each of these ways had its own ups and downs that we had to consider. So migrating a library allowed us to reuse the code that has been better tested over the years. It reduced risks because we can actually do the migration at our own pace. However, it did have drawbacks, but it's quite hard to change any design decision that has been made like years ago for Java without breaking API compatibility. And it also involved quite complex refactoring workarounds, as you can see in the SavedState read and write migration. Most important, the customers, you, hopefully, don't need to migrate their code since you're already using the stable API, so it just works. On the other hand, rewrite the library allowed us to redesign your code with Kotlin and KMP first and start to think about how to handle, for example, on navigation event, different types of events. There was no legacy for us to worry about. And however, that does mean we need more time to achieve feature parity before being able to sunset the previous library. Also, there is the case of missed edge case that can happen. For example, navigation event lifecycle, which we forgot about. And the major drawback is that customers will eventually need to migrate their code once this new API surface is stable. So the best way moving forward depends a lot on the specific details of each library. Sometimes it makes sense to migrate, sometimes it makes sense to rewrite. It will depend on the size, complexity, or how many customers, long-term goals around the library. There is not a single answer for that, but most important, it's to look around all of these things and try to consider what makes sense for you, your team, and for the customers of your libraries. Then make a choice that works best for you. You can also check out the new releases and libraries we talked about today. SavedState 1.3, Navigation Event Alpha 1, and Navigation 3 Alpha 1.
There's also going to be a Navigation 3 Alpha 2 today.
Well, Navigation 2 Alpha 2 today. Hot news. So yeah, if you try them out, please give us feedback, and I would love to hear what you have to say about it. The QR code goes to Navi 3 page. That's all we have for today. Thank you.